In this video, I'm going to show you a cunning trick you can use to determine if this series will converge or if it will diverge. So our normal routine will be to compare this with 1 over n squared, because if you look at the denominator, if you add a positive amount to this denominator, let's say you add 3.2, if you add a positive amount to the denominator, then the denominator will get bigger. Then one divided by something that's bigger, then the whole thing here will be less than or equal to this thing here. For example, if you have 1 over let's say 50 here, and then you add an amount to it, let's say 1 over 53, then this would be smaller or equal to this thing here. So here you're adding an amount to the denominator. So this thing here would be less than or equal to this thing here. Well, if you make this comparison, if you look at this here, let's say, well, by now, whenever you see this, by now you should be able to tell that this thing here will converge. So this thing here, we know it's going to converge. But then this series here is greater or equal to this one here. That means it starts above it. So, but then it doesn't really tell us much, because this thing here we know is going to converge, but then it doesn't tell us much because this series here, this series could still converge or it could still diverge. So it doesn't really tell us much. You see, if you can make this to be above our series here, if you can make this to be above, and then if this converge, then this will also have to converge. It can't diverge. If you can somehow get it to be above, so hang on. So currently this thing here is no good, because wait there, this thing here we know is going to converge. But then this thing here at the moment it is bigger. It is bigger. It starts here. So it could still converge or it could still diverge, because it's bigger. If we can somehow get this to be above it, you see, if you can somehow do this, hang on. Well, this is currently, this line here currently represents this. Let's say if we times by 2, if we times by 2, then it's going to be higher. If we times by 2, it's going to be higher. If we times by 3, it's going to be even higher. If we times by 4, it's even going to be higher. So the trick here is, yes, well, the trick is to, rather than comparing it to 1 over n squared, let's try comparing it to 2 over n squared. So rather than looking at this line here, when we times by 2, we will start here, and hopefully this thing here will be above this series here. So if this thing converges, then the series will have no choice but to converge. It can't diverge, because otherwise this thing here will be above this thing here. But let me illustrate. So rather than comparing it to 1 over n squared, let's try and somehow get it to be less than or equal to 2 over n squared. So hang on. So let's start again. We want to know if so currently, hang on. We tried comparing this thing with 1 over n squared. That doesn't really work, because this is always less than or equal to this. But if we make it to be a 2, there's a chance that this thing here will be bigger or equal to this thing here. So let's make this to be a 2. Let's make it to be a 2. Let's try it. Let's make it to be a 2 and ask ourselves, will this thing here ever be bigger than this thing here? So we want to know, well, what values of n will this thing here always be bigger or equal to, if you want, or than this thing here. So we want to find, we want to know if there's a value of n somewhere where anything above that value, everything this side will always be bigger or equal to this side. So this is a question mark. We are trying to determine what values of n will it be where all values above that value of n, this whole thing here will be bigger than this thing here. So this is a question mark. Let's just assume that this thing here is bigger than this. So hang on, times both sides by n squared, and then later on times both sides by this thing here. That will then give you this. So now from here, take away n squared from both sides. That will then give you this, and then and then and then add 6.4. That will then give you this, and then square root. You see, when we assume that this thing here is bigger than this thing here. Well, if n is bigger than this thing here, then this will be true. Then this will be true. For example, hang on. For example, if you try to ask this silly question like this, hang on. So here earlier we know that if we add an equal amount, if we add a positive amount 3.2 to this, then this will be less than or equal to this thing here. But then so we know that this thing here should be less than this. But if we try and ask this silly question of when would this be greater than this, let's follow the same method here. Times both sides by this, and then times this by this. Times both sides by this. That will then take you to here, and then take away n squared from both sides. That will then give you this. You see, this will be true when minus 3.2 is bigger than 0, which will never be the case. So when you make this assumption here, that would lead you to this. So here, this will never be true. Therefore, this up here will never be true. So going back to here, we want to know when this would be bigger than this thing here. So let's assume this thing here is bigger than this. When would this be the case? Follow through the whole process. It would be the case when n is bigger than this. You see, if you make a silly question like this, when will this be greater than this? Follow through the whole process, and then this will be true when this is bigger than 0, which will never be the case. So hang on. So what we know so far is that this thing here will be bigger than this thing here if n is bigger than this. So we should make this comparison here. 1 over n squared. Sorry, hang on, not 1. 2 over this. But make sure you start at n equals 3. You see, beyond 3, this will always be bigger than this. So all the way to infinity. So in the next video, we're going to make this comparison. Okay.